Hello everybody, my name is Ferdinand Gerhardes, one of the business development managers from the Anritsu EMEA engineering and technology team. Here today I would like to give you a brief overview about the effective isotropic radiated power measurement feature of the MS2090A Field Master Pro. Within this podcast we will introduce the EIRP measurement feature of the MS2090A Field Master Pro. We will start first with the requirement that was set by the 3GPP Technical Specification Release 15. After that, and for a better understanding about the topic, we will introduce some fundamentals about radio frequency radiation hazard safety, in line with a brief introduction into some fundamental antenna parameters. A lot of expressions like ERP, EIRP, power flux density are flying around in discussions. We will describe and define the fundamental mathematics of EIRP in order to understand the measurement procedure of the MS2090A. Finally, we will introduce the measurement feature of the instrument and the operation of the Field Master Pro. Effective isotropic radiated power as it is defined by the 3GPP 5G New Radio Release 15. The 3GPP Technical Specification 13.104 Release 15 Base Station Radio Transmission and Reception is outlining in Annex E the calculation of the effective isotropic radiated power based on manufacturer declarations and site-specific conditions. The usual method of measuring EIRP for base station is to calculate the power by separately measuring the total transmit power and the gain of a single polarized antenna array. However, for 5G G-node Bs, often the antenna and the transceiver are designed in a way whereby a split of the power amplifier and the antenna is usually not possible anymore. Radio frequency radiation hazard safety. In order to protect the population from health hazards caused by high-frequency electromagnetic fields, limits have been set and are specified by the International Commission on Non-Ionizing Radiation Protection and the Federal Communications Commission. They are designed to protect against scientifically proven health risks. The table above shows limits, values that are enforced, for example, in Germany, and based on the Ordinance of Electromagnetic Fields. They apply to stationary transmitters with a transmission power of 10 watts EIRP or more, and for systems of lower power in one location with a total power of 10 watts EIRP or more. The limits for the electric and magnetic field in the second table are based on a 6 minutes averaging interval and apply to fixed installations which generate electromagnetic fields in the frequency range from 9 kHz to 300 GHz. These include fixed mobile base stations, radio transmitters, civil and military radars, as well as amateur radio equipment. All these rules apply to 5G in the same way as for the previous mobile networks. In mobile radio systems like GSM, Edge, UMTS, Wi-Fi, WiMAX, and LTE, the peak value of the transmission power differs significantly from the root mean square value. Not against the classic GSM. Here a modulation with a constant envelope is used. In the other modulation methods mentioned, the peak to average ratio, referred to as a crest factor, is typically 10 to 13 decibels, which is equivalent to the factor of 10 to 20 for the transmit power and for the emissions as power flux density. So, while a base station in classic GSM mode and maximum 20 watts transmit power never exceeds 20 watts, a UMTS base station also with 20 watt RMS power peaks up to 200 watts or 400 watts with 13 dB crest factor. In addition, the number of used transmission channels is multiplying radiated power accordingly. For LTE Advanced, as well as for 5G New Radio, the number of used resource blocks has the same effect as the number of transmission channels, and thus the traffic load. A resource block is the smallest unit of resources that can be allocated to a user. The bandwidth of a resource block is 12 times the used subcarrier spacing of the OFDM modulation. For example, 180 kHz for a sub-6 GHz 5G New Radio signal. For effective isotropic radiated power measurements, it must therefore be ensured that all resource blocks are keyed. Finally, the influence of the directional characteristic of the transmitting antenna, the so-called antenna gain, on the emission is decisive. This directivity substantially increases the power flux density in the main beam direction. The given table shows typical field values depending on the wireless standards. As said before, the power flux density is limited to maximum 10 watts per square meter. The given question marks at 5G New Radio indicate that no final decisions or limits have been yet set, but we can assume, or it let us assume, that the given values will remain plus minus. In the section Antenna Fundamentals, we will discuss in brief the main important characteristica of antenna elements in order to enhance the understanding in the later on discussed problem fields. The performance of the antenna can be described with some fundamental parameters. For our view on the given topic, the antenna gain is one of the main fundamental parameters. The antenna's power gain, or simply gain, is a key performance number which combines the antenna's directivity and the electrical efficiency. In a transmitting antenna, the gain describes how well the antenna converts input power into radio waves headed in a specified direction. The gain is referenced either to a dipole called dBd or to an isotropic radiator called dBi. Due to the fundamental gain of a dipole, the dBd figure is always 2.15 decibels larger than the dBi figure. When no direction is specified, gain is understood to refer to the peak value of the gain. In most of the cases, it is the gain in the direction of the antenna's main lobe. A plot of the gain as a function of the direction is called the antenna gain pattern or radiation pattern of the antenna. Besides, the antenna performance is characterized by a parameter that is called half power beam width, which is the angle between the half power, the minus 3 dB points of the main lobe, when referenced to the peak effective radiated power of the main lobe. Not very important for our topic here, but the front to back ratio is referring to the ratio of the power gain between the front and the rear of a directional antenna. Finally, the so-called first null in degrees, or the level of the first side lobe, are important parameters in horizontal and down-tilt radiation direction. These parameters are important on the background of the aforementioned Federal Emission Control Act in the Ordinance on Electromagnetic Fields, because here a safety distance is defined in antenna bore side and vertical distance direction. For the understanding of the given topic, it must be clear that the radiated power of the measured antenna will always be a simplified view on a very complex topic. In general, an antenna is always radiating into a three-dimensional sphere. It would be correct to take power measurements at infinitesimal points around this sphere in order to get the figure for the so-called total radiated power of the antenna. As this is very complicated and more a method of measurements in an anechoic antenna chamber, we simplify our view onto the topic. In practice, we cut through the three-dimensional antenna pattern along a specific two-dimensional plane and define this as a representative antenna pattern. Usually, these 2D planes are in the bore side direction of the azimuth or elevation direction of the antenna. What kind of antenna can we consider in practice? What kind of beam widths and what kind of gain do we see in the field? For the moment, we don't have a common answer to this question, because no network is really in commercial operation so far, and the antenna manufacturers keep information often very confidential. But since spring year 2019, beamforming antennas in the sub-6 frequency range 1 and trials for the frequency range 2 at 28 GHz are becoming visible. Public available information reveals some details about the typical 28 GHz TRP, a so-called transmit and receive point from Ericsson. It is the EIR 5121 transmit and receive point. The vendor is specifying an EIRP of plus 46 dBm, which is equal to 40 watt. Later on in this podcast, you will see how it is possible to check and verify such values with over-the-air or OTA called measurements in the field. The antenna beam width is here in our case specified and symmetrical to be 12 degrees. Here we have another example for a highly integrative AAS, active antenna system for frequency range 1, without any RF connector anymore. It is the Ericsson EIR 6488, a theoretical maximum EIRP value of plus 77 dBm, depending on duty cycle and power tolerance is possible. Based on the before mentioned limit of 10 watt per square meter, the resulting safety compliance distance in bore side direction would be here approximately 20 meters. This value is based on a 75% duty cycle and a maximum power of 200 watt. Effective isotropic radiated power definition and calculation. Equivalent isotropic radiated power can be defined as the power in a given direction and with a relative antenna gain with respect to the antenna gain of an isotropic radiating element multiplied by the net power accepted by the antenna from the connected transmitter. Usually, we will have some problems to get the correct net accepted power of an antenna element for a 5G G-Node B. This is due to the fact that either no test ports are available, but more the fact that the 5G active antenna elements are used. In such cases, every antenna element has its own power amplifier for transmitting and its own low noise preamplifier for receiving. There might be no test ports available at all. As discussed before, we are assuming that we are in the bore side direction of the antenna beam in azimuth as well as in the elevation, in the down tilt. For any kind of reliable and repeatable measurements, it's therefore wise to use an antenna tripod together with a spherical printhead for measurement antenna. Besides, the knowledge of the measurement antenna K-factor is beneficial. The K-factor in dBm per meter is necessary to convert the antenna voltage, which is measured with a spectrum analyzer or calibrated receiver connected to the antenna, from dB microvolt to a field strength value in dB microvolt per meter. In this slide, we underline again the problems that may arise under practical conditions when we try to find the point of maximum radiation at the actual measurement location. Being a little bit off from the correct antenna bore side and down tilt angle will easily cause measurement deviations of a couple of decibels. In the same will arise when they are not correctly located at the azimuthal bore side angle. Trying to overcome to repeatable results by steering the antenna by hand will for sure be not successful. Under free space conditions, the Friese transfer formula can be expressed as given on the slide here. According to the definition of EIRP, the calculation formula of effective isotropic radiated power can be derived. The precondition of the establishment of this formula is that the distance of the transmitting and receive antenna satisfies the far field measurement condition. From a transmitter perspective, EIRP can be expressed as a delivered net power to the antenna connector multiplied by the gain factor of the antenna. This is equal to adding the values in a logarithmic scale. From a receiver perspective, the same EIRP can be expressed as the received power plus the free space loss plus additional losses in the measurement setup like cables and connector minus the gain of the receiving antenna. This way, EIRP measurement is implemented in the MS2090A measurement feature. Finally, you can calculate the free space loss. Now you have everything on hand to come to some useful practical results. In the previous section, we have seen some examples that the maximum allowed EIRP power is given as an absolute power and related to milliwatt, a dBm figure. It can also be defined as a radiation flux density in watt per square meter, because the RF radiation hazard safety limits are based on exposition rates and power flux density. With the knowledge of some fundamentals, it is relatively easy to convert one figure into the other. The power of a transmitter that is radiated from an isotropic antenna will have a uniform power density in all directions. The power density at any distance from an isotropic antenna is simply the transmitter power, Ptx, divided by the surface area of a sphere at a distance of r. This means that every doubling of the transmitter distance is reducing the power density by a factor of 4. Let's make a quick example. Let us assume an isotropic antenna at 3.5 GHz, which is fed with a net power of 100 watt. The resulting power flux density in a distance of 200 meters would then result in 400 microwatt per square meter. In case of using a directional antenna with an isotropic gain of 10 dBi and fed with a reduced net power of 10 watt, the power flux density is resulting in the same value. This is due to the fact that less power is more focused into a specific direction. Now, let us assume we are having a spectrum analyzer in our example, and we are measuring a 100 MHz wide channel power, for example, of being minus 32 dBm, using a directional logarithmic periodic receive antenna with an approximated antenna gain of 7 dBi at 3.5 GHz. Also, this result is finally an EIRP of 100 watt or plus 50 dBm. Finally, let's summarize what we have heard about now about EIRP. Active antennas can be steered over a wide arc, typically 60 to 120 degrees, with a narrow focus beam of 5 to 15 degrees. For initial field trials, there is a need to estimate peak EIRP direction relative to expected direction and/or bore site. Operators also need to understand the angles of the nulls and the side lobes so that they can minimize interference between adjacent cells and their traffic. Investigations are ongoing at the moment using an Anritsu MS2090A ultra-portable spectrum analyzer on a drone to automate such measurements. Remember, EIRP is only valid as long as you comply with the so-called far-field distance criteria. Further on, the value is dependent on accepted net power, antenna gain, theta and phi being the same as azimuth and elevation direction, free space loss, polarization loss, and steering loss. At the end of this podcast, we will talk about how the aforementioned features have been implemented in the MS2090A Field Master Pro. Remember, 5G in your radio is in most cases a time domain duplex signal, which is heavily dependent on traffic load and used slot formats. For a stable measurement readout, we have to apply a so-called gating aperture. This way the signal becomes stable and we can integrate the power of the spectrum trace and thus getting finally a channel power number. Select the 5G in your radio analyzer mode and select finally the channel power menu. After you have set the correct signal parameters, you can see that the green button in the top right corner is becoming green. This is indicating that the Field Master Pro has synchronized with the time domain duplex signal. Now you can switch to the EIRP menu. Remember the discussed parameters that are important for our EIRP measurements: distance to the antenna site and the gain of your receive antenna. Be aware to point with your antenna to the vertical polarization direction. Now you can see in the bottom of the screen your EIRP measurement results. But also be aware that most of these antennas are using slanted polarized antennas, so it might be wise to repeat this measurement for the minus 45 degree direction as well as for the plus 45 degree polarization direction, and then finally to combine vectorially both results. Finally, a user can switch to the so-called quick view screen. This representation is reducing all parameters to the most wanted outcome. Here on this slide we can see a real measurement example. The site was approximately 200 meters away from the measurement location. The resulting effective isotropic radiated power was around plus 48 dBm in a distance of 200 meters from the antenna. As said before, the quick view representation delivered an overview about EIRP parameters. There are also other measurement features in the 5G new radio operation mode available. Just as one example, we can show that the measured 5G cell provided just one antenna beam instead of expected usually 8. You can learn more about this measurement feature in the Anritsu podcast MS2090A. Grid of beam measurements are discovering the performance of a 5G new radio cellular communication. Finally, we would like to mention some references that are useful for reading on the background of our given topic. Thank you very much for viewing our podcast. This podcast was part 3 of a MS2090A podcast series. Beside the presented topic, you can select in addition one of the following podcasts from our YouTube video website in order to learn more about the features and possibilities of the MS2090A Spectrum Master Pro. One of the first topics is kicking off a new graphical user interface experience for future-proof man-machine interaction, followed by grid of beam measurements discovering the performance of a 5G new radio cellular communication, and then finally an insight into the beneficial use of real-time spectrum analysis for identification of elusive signals. Thank you very much for your attention. Looking forward to see you soon.